Evening, everyone. Today, I wasn't supposed to be here. Tonight was supposed to be the Motley Crue show in San Diego. So that's where I was supposed to be.
Where are you supposed to be?
Down at the Motley Crue show.
Oh, today?
That's the San Diego show is tonight.
Yeah, man. Sorry.
So that's a bummer. Anyway, so we'll see. All right, so what I wanted to do tonight was cover at least a couple sections. And then for this upcoming assignment, there'll be a natural separation between learning all the basics of this stuff, and that's kind of what we're doing right now, versus applying it to things, okay? So let me share the screen here. And there we go. That was me giving my Math 30 prop class a question that got away from me. So 185. Today we're doing alternating series and ratio and series there. Ratio and root test. Okay, now since I've got all these things saved like this, I'm much more organized than I was, you guys remember. Whoops.
It's forcing you to be organized.
Yeah, what happened here? There we go. Cancel. Still broadcasting?
Yep.
Okay. Yeah, so if you get kicked out or if you miss something or whatever, you know, after class, some Zoom class is over, I can, what the hell is that? Yeah, undo that. I can just go back to these notes and, you know, maybe there's some particular example that you want to see or something like that. Hair on my screen. Okay. So yesterday we were talking about the comparison tests. So the comparison tests. And the workhorse was the straight comparison test, where if we had a positive sequence of numbers, two positive sequences of numbers, then if the sum of the b's is finite, that implies the sum of the ands is finite. And it also said if this guy adds to infinity, then that would imply that this guy adds to infinity. Maybe today, certainly tomorrow, we're going to do a really hard problem in one of these sections that all of our slick and clever tests don't work, and we have to go all the way back to this stuff. Okay, and then we had a limit comparison test. These things, there was 3 conclusions to this, but only ever really used the first one. If I have 2 sequences of positive numbers, okay, and if the limit as n tends to infinity of this ratio, which is C, all it needs to be is a positive real number, then if that, then the two series AN and BN do the same thing. Meaning they're both going to converge or they're both going to diverge. Okay. So when we were looking at one of the harder problems at the end of the night yesterday, which was figure out if this thing converges or not, you know, we can't use the integral test. We can't use, you know, the integral test, dx over, I mean, what the hell do you say here? X factorial, if to get the gamma function out for that mess. So, you know, that's a big what if. We ended up using a comparison test on this thing. Okay. So that's kind of our quick review here. All right. Now, in section 11.5, that's where we are today. That's the new stuff. And it's the alternating series. Okay, now, I do know a bit of the history about these things. So, long time ago, you know, when people were having to navigate and, you know, by taking readings from the stars at night, like, you know, if you were on the trade route from, let's say, Baghdad to somewhere else that's really hot, you know, you're going to be walking at night, so you're going to need to like navigate. If you're near the coast, you know, and you're going to be in boats, and then you can navigate. So coming up with approximations for what the sine of x is and what the cosine of x is, people started seeing things like, well, it seems as if I use this approximation for sine x like so over, I think that's going to be 120. What happens here is this series is alternating. Okay. Another thing that you could look at would be this geometric series. Like, let's say n is going to go from 0 to infinity. So if you did negative x to the n, as long as the magnitude of x is less than 1, then this is equal to 1 over 1 minus negative x. Or to state it another way, 1 over 1 plus x is equal to 1 minus x plus x squared minus x cubed plus x to the fourth minus plus. And if we use our rules for exponents, we get this series that alternates back and forth between positive and negative. Okay. Now, I don't know who was the first person to figure out, like, if we were to add up the first n terms of a geometric series, k equaling 0 up to n of, we're going to say x to the k, it's going to be 1 minus x to the n plus 1 over 1 minus x. I think it goes back to medieval times. And again, you know, my thing with the Templars and their banking system, to do any kind of interest calculations, you're going to have some familiarity with this formula. unless you're just going to have stupid interest. Like, okay, every year that you keep your shit in my bank, I'll give you $10. Well, maybe it got more appealing because these guys were dealing with kings, and maybe it got more appealing for them to do normal interest. So anyways, you can imagine then, look, you know, a person that's kind of more inquisitive than other people and be the kind of person that doesn't go home and play on their PlayStation. Instead, they go home and like deal with math stuff. Someone would have looked at this and said, you know what? This piece right here, if we let this go to infinity, if that's less than 1, it's going to go to 0, and you get this nifty formula. Okay. Okay, so this is an example of an alternating series. Okay, now there are series that don't alternate and have negatives and then some positives, and I can show you how to make some of those. Ooh, some swim team was practicing today in Irvine, and they got busted. Wow. Okay, so like I said, there will be some series that I can, you know, have it be positive for a little while, negative for a little while. So in general definition, okay, let's let A sub n be a sequence with A sub n being positive for all n, then an alternating sequence is a sequence of the form the sum -1 to the n, a to the n. Okay, now I'm intentionally being vague with where I'm starting. Notice that I'm not writing anything down. Okay, like n equals wherever, because sometimes you start with a negative, sometimes you'll start with a positive, but this is like just the most vague thing we can come up with. Okay. All right, so the natural question here is, when will this converge? So the question that we want to answer is, when will this alternating series converge? Okay, maybe we can come up with something. Okay, well, first of all, if this thing is going to converge, then we know the limit as n tends to infinity of an is equal to 0, right? That was the criterion for convergence. Okay. All right. Now, if the limit is equal to 0, we want to make sure that there's a couple ways something can go to 0. Okay, like you could be doing this, like some kind of a squished sine curve and really coming in. Okay, so if we were to look at like the nth partial sum, okay, so blah blah blah. Okay. So let's look at S sub 2. Okay, now in my notes I wrote B sub n, so I might mess up and write B. Okay, so this was going to be, let's say we're starting with positive, guys. So it's going to be A1 minus A2. Okay. Then what we're going to do is we're going to look at S4. Okay, now I'm sure Leibniz, he's the guy that came up with this test. I'm sure he monkeyed around with just ideas. I've watched many YouTube videos about like Ken Rebay, the guy that basically paved the way for Andrew Wiles to prove Fermat's last theorem. I mean, he needed to prove something called the epsilon conjecture, Serre's epsilon conjecture. So he just started looking at simple cases. So I would imagine that Leibniz maybe started looking at simple cases. And he's thinking, all right, well, this is equal to S2 plus A3 minus A4. Okay. Now we're going to be creating a sequence of these things. Now we have some experience with this during a normal circumstances semester. You know, we'd be meeting twice a week, but even if we were in person in the summer, this stuff, it's a little, it can be a little rough to digest. So what Leibniz must have realized is that if A3 is smaller than A4, i.e., if the sequence AN wait, I have this backwards. If why does it keep doing this? Okay, so if this number is negative, meaning A3 minus A4 being negative, that would mean that A4 is smaller than A3, i.e., if come on, there's got to be a control for that I can touch. If A4 is less than A3, i.e., if AN is decreasing, okay, then what he recognized is that S4 is bigger than S2. Okay.
Isn't A4 greater than A3 if it's negative?
No, the A's are all positive. There's no, all the A's are positive. The negative comes from the -1 to the n.
Oh, okay.
So remember how this works? The alligator's mouth opens to the bigger person. Okay, so A3 is larger, A4 is less. Okay, so then what he starts playing around with, like he looks at S sub 6. And he writes it as the A1 minus the A2 plus the A3 minus the A4, groups all that together, plus the A5 minus the A6, realizes that this is S4 plus A5 minus A6, and that is larger than S4 because A5 minus A6 would be positive And so S4 plus something is bigger than S4. Okay, so he continues on doing this, and he gets a sequence of numbers. And this sequence of numbers, which is this S sub 2n, where the property satisfied is that S sub 2n is bigger than S sub 2n minus 2. Okay. Okay, now S sub 2n, that's the A1. Then it's going to be minus the A2 plus the A3. See what I'm doing here with the distribution? Minus A4 minus A5 minus . Okay, now here's this step. B sub, no, not B. I knew I'd fuck that up eventually. A sub 2n minus 2 minus A sub 2n. Okay, now remember that the sequence is decreasing. Okay, so the AN is decreasing. Okay, so this number A2 minus A3, so that's like 1/2 minus 1/3. So this is a positive number. This is a positive number. All of these are positive numbers. So that means that's less than or equal to A1. So the conclusion is this sequence is bounded above and increasing. Okay, so there exists an S such that the limit as n goes to infinity of S sub 2n is equal to S. Okay, so then you do some kind of argument by letting m be some number. Anyways, you conclude what you then do is you do the odds. Okay, but that's more for Eduardo as a junior. Okay, so anyways, you conclude that the limit, or any k goes to infinity, of S sub k is equal to S, i.e., here's what we have just established. And this is called the alternating series test. And give me 1 second. You guys catch up. I gotta shut this gate or it'll slam, squish the dogs. All right. So here's what we just established, is that let's let B sub n be a sequence that satisfies number 1, the Bn is positive for all n, just to make sure we actually have an alternating series. 2, the limit as n tends to infinity of Bn has to equal 0. And 3, if Bn plus 1 is less than Bn for all n, then the series that's called the alternating series, -1 to the n, b to the n, converges. Okay, so that's all you need for an alternating series to converge. That's it. All right, so like, just to give you an example of this, let's say I'm going to look at this series. Now we know this is diverging. It adds up to infinity. We've proved it a few times. Okay, but if we consider this series, n equaling 1 to infinity, and if I want to start it with positive guys, we'll do it like this. The b sub n, which is 1 over n, it's decreasing down to 0. So that means this series converges. Okay, so having the thing alternate apparently is enough to get this guy to converge. Okay, now what's going to be a topic in a little while is we're going to talk about some kinds of convergence are stronger than others. All right, so this section is just a piece of cake. All right, so you just do the exercises and you just look and see if the limit is 0. Okay.
Could you scroll
So-
up for just a second, please?
Scroll up.
Thank you.
Okay. Okay, so, really this is, real easy. Just do one example. Take something out of the book. But really, where we really want to get to here is with the estimations. Okay, so this guy, n equals 27 to infinity, -1 to the n over the square root of n converges. The reason is because, well, it's easy for an alternating series to converge. Okay, now here's where the interesting stuff starts to come into play. Okay, the estimation of sums. Okay, so here's where we're going to get a real good taste of the power of mathematics. We might not know what an infinite series adds up to, only that it adds up to something. But what we're going to learn is under certain circumstances, like especially for alternating series, we're going to be able to get arbitrarily close to whatever it is we're doing without even looking, without even knowing what it is. Okay, so I have a series, and it's probably where the BNs are positive. Now, again, I'm going to be vague with the, am I starting at, where am I starting, where am I ending, okay? Now recall that the nth partial sum, Sn, is equal to the sum k starting somewhere and going up to the n of -1 to the k bk. Okay. Now what we want to do is we want to call Rn the rest of it. So now that's going to be the sum from n plus 1 to infinity, -1 to the k, b sub k. Okay, now, if the series converges to, let's say, S, then we have S is equal to Sn plus the rest of it. Okay? Okay, so what did I say is? If this thing converges to some S, then that's what we would have. Okay, so the remainder piece, this is going to equal the S minus the Sn. So this is the error in the approximation. Okay. All right. Now, if you knew what the number was, S, exactly, then you would know what your how far off your approximation is. But the question then becomes, well, why would you even approximate it in the first place? Why wouldn't you just use the real number S? Okay, well, let me tell you. So is the real number pi programmed into your calculating device? Is it?
Yes.
You sure? How many decimal places does pi go out to before it repeats itself? Pi is an irrational number, right?
Exactly.
So, like when I was in high school, my calculator went out this far. Okay. Now, probably somewhere in the memory, once I went to college and I learned some more shit, somewhere in the memory, they probably stored the next 8 or whatever, however many I have here. So I think the next 926, I think it goes 5258. I think kind of like a nerd off right now.
It's
No,
5-4.
5458.
Yeah.
Okay, so I lost the nerd off contest then. 5, 4, 5, 8, and whatever. Okay, so I learned later that that our devices are going to store more, but they're just not going to show them to us because the display won't allow it. Okay, so even with our powerful iPhones that are more powerful than the computers that put people on the moon in 1969, and I might argue more powerful than the computers that put those rovers on Mars back in I remember it was the 4th of July, 1998 or 97. No, it was 90.
Yeah, it
Well,
was
whatever.
98. Yeah.
98. Yeah, there
Yeah,
weren't any
98.
iPhones back then, right?
No, we still have the bricks, those giant shoe-looking things.
I don't think there was any cloud computing or any of that stuff. Okay. All right. So, but even with our powerful devices, pi, it would take an infinite amount of memory to store it all. Okay, so even in our devices, we do this. Okay, now what I'm going to do here is I want to figure out what the magnitude is of the error. So that's going to be the S minus the Sn. So this is going to give us the magnitude of the error. So when I write in what this is, Rn, it was the sum k equaling n plus 1 to infinity of -1, and I don't know, how do I want it? Well, I'll put an n here, and if I need the n plus 1, I'll put the n plus 1. Okay, b sub k. All right, so as I start to write all this shit out inside the absolute value sign, what I get is -1 to the n plus 1, b sub n plus 1, and then plus -1 to the n plus 2, b sub n plus 1, plus, I think 3 will be enough. No, I probably need 4. -1 to the n plus 3, n plus 1, n plus 2, n plus 3, plus -1, n plus 4, bn plus 4, plus ... Okay, now I'm going to do something here that I'm not exactly sure if I'm allowed to do this. Remember, I said the rules of algebra don't really, the rules of arithmetic sometimes don't apply when you have infinitely long sums. Okay, we've assumed this series is converging. So we are assuming that the bn's go to 0. So the next step is a little bit skeptical. Okay, I'm going to factor this x to the n plus 1 out. Okay, now what I have left is going to be b n plus 1 minus bn plus 2 plus bn plus 3 minus bn plus 4 plus bn plus 5 minus plus, like that. Now the absolute value of -1 to the n plus 1, that just goes away. So this ends up being b sub n plus 1. Okay, then it's going to be minus b n plus 2 minus b n plus 3. So what I did is I grouped these guys and I factored a negative out. Now I'm going to do the same thing for the next pair. B sub n minus 4, plus 4, minus b sub n plus 5, minus ... Okay. Okay, so now I did something even more sketchy. Because factoring something out, maybe one could say, okay, well, and I would have to get into an epsilon delta proof and all of that stuff. But what we're going to learn here is this kind of convergence is actually very weak. Okay, so any event, what's a bigger number, bn plus 2 or bn plus 3?
bn plus 3.
It's a decreasing sequence, remember? Oh. So this guy's bigger, so that guy's positive. This guy's positive. This guy's positive, right? Okay. So this is that, wait, hold on. Wait, I missed a step. Hold on. Okay, wait, start over. I missed a step. There's a way I'm going to get rid of the absolute value. Okay, so the Rn, let me write it again real quick. Okay, in magnitude is the magnitude of Bn plus 1 minus Bn plus 2 plus Bn plus 3 minus Bn plus 4 plus minus ... Okay, now if I use the associative property here, which, as I've been telling you, maybe I shouldn't be doing this, and like this, okay. Okay, this is a positive number. That's a positive number. Everything's positive here, so I don't need the absolute value sign. Equals Bn plus 1 minus Bn plus 2 plus Bn plus 3 minus Bn plus 4 plus Bn plus 5 minus Bn plus 6 plus ... Okay, now again, I'm going to use my associative law that I'm skeptical to use. And then it's going to be minus Bn plus 2 minus Bn plus 3. So I'm reassociating minus Bn plus 4 minus Bn plus 5. Minus. All of these guys are positives because it's a decreasing sequence. Okay, so we arrive at the amazing conclusion okay, that if this alternating series, -1 to the k, b sub k, converges, and if Sn is the estimate we're going to use up to n of -1 to the k b sub k, then the magnitude of Rn, which is the error in the approximation here, according to what we just concluded, this thing is this number minus a positive. So it's going to be less than Bn plus 1, all right? So that means that the error term, come on, stand like goddamn pencil, is less than the Bn plus 1 term. All right?
So that would be the answer for that?
Well, that's how you estimate the sums.
Oh, okay.
Okay. All right. So let's do this one. So, for example, we know that this sum of -1/2 to the n adds up to 1/1 minus a half, which is 1 over 3 halves, which is 2/3. Okay. So what I'm trying to do here is verify the result. Okay. All right. So my series is K equaling 0 to infinity. And then it's going to be -1 to the n, 1/2 to the n. Okay. Okay, now let's say I want to use S10 to estimate this number. Okay, to estimate 2/3. Okay, so S10 is going to be, I started 0, 1 minus a half plus a fourth minus 1 over 16 plus 1 over 32, 64, 128, 0, 1, 2, 3, 4, 5, 6, minus multiply that number by 2 and get what?
165.
No, 128 by 2. 256.
256. Oh shit. Yeah.
256. Then you multiply this number by 2, and it's going to be the 512. 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I need 2 to the 9th and 2 to the 10th. So
1,024 and 2,048.
so minus 1024 plus
2048.
2048. Okay, so let's see here. Let's try this out. Clear, get out of that. All right, so I'm going to have 1 minus 1/2 plus 1 over 4 minus 1 over, I missed an 8th. Fuck. 1 minus a half plus a fourth minus an 8th plus a 16 minus a 32 plus a 64 minus the 128 plus the 256 minus the 512 plus the 1024. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So start over. 1 minus a half plus a fourth minus an 8th plus a 16th minus 1 over 32 plus 1 over 64 minus 1 over 128 plus 1 over 256 minus 1 over 512 plus 1 over 1024. And checking, you guys wanted me to check some of your test questions. I've got to get my TI-85 working. I mean, that calculator is just the greatest. Anyways, what I get here is 0.6669921.875. That's pretty damn close to 2/3. Okay. Now, according to our thing, R10 is going to be less than Bn plus 1. So that's going to be 1/2 raised to the 10 plus 1, which is 1 over 2 to the 11th. Okay. So if I was to subtract 2/3 from this number that I got on my calculator, oh, fuck. 0.666992187.5. If I subtract 2/3 from this number, I'm going to get S10 minus 2/3. The actual number is 0.000325. And if we look at 2 to the 11th, 2 raised to the 11th power, and flip it over, is 0.000488. So by design, it worked. The error can be no bigger than this number, and it worked out for us. Okay. And then you get problems like this, like, for example, the alternating harmonic series converges -1 to the n plus 1 over n. Okay, so how large should n be so that the magnitude of the error less than 0.0001? Like, let's say we want 4 decimal places of accuracy. So these are real easy problems. Solution, we know that the Rn is less than the Bn plus 1. Which is equal to 1 over n plus 1. Okay, so set 1 over n plus 1 to be smaller than 0.0001. So that n plus 1 must be larger than 10, 100, 1,000, 10,000. So n has to be bigger than 9,999. So pick n equal to 10,000. So in order to approximate this with the accuracy that we want, we're going to have to go out 10,000 terms. Okay, so that's telling me that this guy isn't converging very quickly. There are other series that converge quite rapidly. All right, let me go get my water filled up so you guys catch up there for a second. So before I go on and do something new here, isn't the natural log of x, one way you can define the natural log of x would be from some antiderivative, maybe go up to x of 1 over t dt. This is one way that you can define the logarithm, is the antiderivative. Integrals are sort of like adding up a bunch of numbers, aren't they? Isn't that kind of what happens? You're adding a bunch of numbers up and then you take a limit. So it's sort of like adding up things. Okay, so the logarithm is very closely associated with this guy. Okay, so what I want to do is maybe try to figure out what that sum is. Okay, so let's see here.
So that would be like ln of x equals the limit to from 0 to x over 1 of sub t.
Yeah, so here's the problem. Okay. I want to find what this sum is. N equaling 1 to infinity of -1 to the n plus 1 over n. We know it converges. I want to see what it's going to converge to. Okay, so let's see here. Euler started adding up these numbers. Okay. After he solved the Basel problem, then he started to add these things up. Now, Euler had a brain like no other. All right. And so he probably could tell something was up. Okay. So this is going to be done in steps. Step 1, we're going to let t sub n be a sequence where I'm going to define each one, this guy as 1 plus a half plus a third plus a fourth all the way up to plus 1 over n. And then he wants to subtract off the natural log of n. Okay. He sees that the alternating series converges, but it just creeps out. Okay. The harmonic sum series adds up to infinity, but it creeps out there. In order to get that sum bigger than 10, you need to have more than e to the 10th number of calculations just to get it bigger than 10. Okay, so it goes to infinity, but it creeps out there. Euler also knew that the logarithm is a very similar thing. It goes to infinity, but it creeps out there. So he was kind of thinking that this guy might be moving to infinity at the same pace as this guy. Okay. So the goal here is to show that the limit as n tends to infinity of Tn exists. So I'm going to draw a picture here. And I'm out here on the x-axis, and we've gone way out here, x and the y-axis. And I'm going to let f of x be 1 over x. Okay, and then it's going to come down. We know this guy does this kind of thing, right? Okay, now this point I'm going to call n minus 1. This point I'll call n. This guy I'll call n plus 1. And maybe this guy I'll call n plus 2. Okay. So now what I'm going to do in red I'm going to draw some triangle or rectangles that are going to be sitting above the picture. Okay. All right. So the integral from, I got to draw another picture. Okay. Then the next guy, I got to draw the first part of it. Normally in the board, I can do this a little differently. Okay, so here's the 1, here's the 2, the 3, the 4, the 5, and so on. Okay, so the function is coming down like this. Okay, so we draw the rectangles above. We need to first get some kind of a estimate of what's going on when the thing starts. Okay, so from here, we can see from the picture the integral from 1 up to n of 1 over x dx, which is the natural log of n, by the way. This is smaller than the area of all of these rectangles that we're adding up. Okay, i.e., the natural log of n the natural log of n is smaller than 1 plus a half plus all the way up to 1 over m. Okay? So what all that told us there, and I'm going to go back to the above picture in a second. Okay? Actually, I'm going to draw it underneath. So what we've just established is that Tn, which is 1 plus 2 plus 1 over n minus the natural log of n, is positive for all n. Okay? Okay. And Tn, because it's positive, is bounded below. I told you that one result that we had that used the completeness axiom, so they're going to show up a few times. Here it is showing up again. So the Tn guy is bounded below. Okay. So if I was to draw the rectangles now differently, so I'll draw one big guy like this. Go there. And I'll do the rest there. Yeah, that sucks. See, it's all crooked. Maybe I should switch to that notability thing. Fuck, I know what to do. Turn it vertical. Problem solving skills. Yeah, that worked really good.
The shapes, doesn't it
Got
have
low on.
up there?
Yeah, it does, but I don't know how to work it.
Uh,
All right, well, anyway. And in the middle here, we're going to have a place where it's going to go. Okay, so this picture is going to come down like this. Okay. And here's 1, here's 2, 3, 4. And then over here is n minus 1, n. n plus 1. Okay, so now in blue, I'm going to draw rectangles underneath the thing. Okay, now this is where I always kind of get confused a little bit. Well, most of the time. Let's see if I do it again. God damn it, it just fucking, oh wait, undo. Yeah. Okay. Pencil, you fucker. Okay. I'm going here. And then I'm going here. Okay, now from this picture, the area of this box,
It's
yeah. Okay. The area of this box is 1 over n plus 1. Okay. Now, the area of that box, which is 1 over n plus 1, is less than the integral from n to n plus 1 of 1 over x dx, which is the natural log of n plus 1 minus the natural log of n. Okay? So what we can say from all of this, because this number on this side is bigger than this number over here, then the natural log of n plus 1 minus the natural log of n minus 1 over n plus 1 is positive. Okay? So now I want to investigate back to this sequence Tn. I'm going to consider Tn minus Tn plus 1. Okay. Now, if I can show that this is positive for all n, that would mean that Tn is a decreasing sequence whose bounded below, therefore, will have a limit. Okay, so we write in what it is. Okay, so it's going to be this guy, 1 plus a half plus a third, all the way up to 1 over n minus the natural log of n minus that whole same list, 1 over n, but then I go to the next one, and then I subtract off the log of the next one. Leonard Euler was a very clever fellow. Okay, now these are finite lists, so I don't have to worry about doing stuff. A bunch of things cancel, and what we're left with is this thing that we looked up above, this thing, minus this guy, minus 1 over n plus 1 is positive. So my sequence Tn is a decreasing sequence bounded below. So the limit as n tends to infinity of this sequence exists. Okay. So we call this limit as n tends to infinity of this Tn, this, which is known as the Euler constant. Okay, so at 7:16 on Wednesday, July 22nd, you just learned a new important number in the universe. It's the Euler constant. Okay, so if you write out what the Euler constant is, it's equal to the limit as n tends to infinity of the harmonic series nth partial sum minus the natural log of n. Okay? So his reasoning, his thinking is this: that infinite sum is going off to infinity at maybe this pace. Maybe not that pace. The natural log is going off to infinity at like this pace. What he found was that the nth partial sums of the harmonic series are going to infinity at the exact same pace. Okay, so the harmonic function and the logarithm seem to have some kind of a connection. All right, so that's the Euler constant. All right, now we need to figure out what that thing adds up to. Okay, so now we're in step 2. Use this thing to find what the hell this sum is. Okay, and it's not a waste of time to figure this out, because this is sort of like one of these important series where if you take away the -1, it's going to diverge. So apparently just having it alternate makes it converge. Okay, so what I'm going to do is I'm going to let h sub n be the following. Let me write it as a sum. Okay, it's going to be the sum of the partial harmonic series, 1 to n of 1 over k. Okay. And we're going to let s sub n be the sum, k equaling 1 to n of -1 to the k plus 1 over k. So if I was to consider h sub 2n minus h sub n, okay, well, let's see here. I'm going to do it in a line. Okay, so here's the hn. It's 1 h sub 2n, a half, a third, and then we get to n minus 1, 1 over n plus 1, and then 1 over plus 1 over 2n minus 1 plus 1 over 2n. Now I'm going to subtract off the hn. Okay, so I'm going to put the 1 underneath the half. I'm going to put the half. Shit. Let me. I need more of these things. Okay, so it's 1 plus a half plus a third plus a fourth, a fifth, a sixth. Okay. Okay, so I'm there. Now minus, I'm going to put the 1 there, the 1/2 there, the 1/3 there. You get the idea? Okay. And then the 1 over n there. So I'm dropping the numbers over all of, underneath all of the even guys. Okay, so this list ends up being 1, 1/2 minus 1/2 is that, and then the 1/3 left alone, and then minus 1/4. A 5th doesn't do anything, but this goes to minus 6, plus minus dot dot dot. Then it's going to be the 1 over 2n minus 1 over n is minus 1 over 2n. And what we see is this is s sub 2n. It's the actual 2nth partial sum of that guy. Okay, so what we have got here is that s sub 2n, by the way, guys, I don't think we're going to do another section tonight. I have to save it for tomorrow. I forgot I had to do all this Euler stuff because we need it. Okay, so the s sub 2n is that thing. All right. So from step 1, the limit as n tends to infinity of the hn minus the natural log of n is equal to the Euler constant, because hn is this thing that Euler did. He added up to n, and then he subtracted off the log. So the hn is just to add up that part stuff. Okay? And so if that's the case, by doing a variable substitution, the limit as n tends to infinity of h sub 2n minus the natural log of 2n would also be the Euler constant. Okay, now here comes a bunch of manipulating. S sub 2n, which has been established to be h sub 2n minus h sub n, is equal to h sub 2n plus 0 minus h sub n. Okay, so now I'm going to insert something for 0. H sub 2n minus the natural log of 2n plus the natural log of 2n minus the h sub n. Okay? Now this can be collected up as h sub 2n minus the natural log of 2n plus the natural log of 2 plus the natural log of n minus h sub n. Okay. That is equal to h sub 2n minus the natural log of 2n plus natural log of n minus hn plus the natural log of 2. So the limit as n tends to infinity of s sub 2n, which, by the way, folks, is the infinite series from 1 to infinity, the alternating harmonic series. It's the limit of all of this stuff as n goes to infinity of h sub 2n minus the log of 2n natural log of n minus hn plus the natural log of 2. But hold the cannolis here. That is, I got to do something here. Pull the minus sign out. Minus sign. Got to rearrange these two guys. Minus hn minus log of n. Okay. Anyways, that's gamma minus gamma plus the natural log of 2, which gives us the log of 2. So our conclusion here is this sum from 0 to infinity, the alternating harmonic series, it adds up to the natural log of 2. So there's another one that we have been able to figure out. Okay. All right. Well, in the exercises in 11.5, I mean, I would say try to do lots of these things. Being able to apply this stuff is going to be important in your future. It's you know, for where we're going with this stuff, for you engineering guys, everything is this, you know, power series stuff. Okay, well, anyway, so do a bunch of those problems. All right. Okay, so let's start off the next section, and we'll probably finish it tomorrow. This is a very important section. The main tests that we use for everything are in this section. So, where's the paper clip for it? Okay, so the next section, 11.6, absolute convergence and the ratio and root tests. Okay, so we'll start off by what it means to be absolutely convergent. Okay, so definition. Let's let AN be any sequence of reals. It might alternate, might be all positive, it might go positive for a little bit, negative for a little bit. The way you do stuff like that is you put up in the top like sine of pi over like maybe
Over 3.
maybe put a 10 here.
Oh.
Or maybe put 100 here. Like,
Okay.
So you do like the sine of n pi over 100. Okay, so when n is 50, when n is 0 and goes to 50, the sign is, this is going to be positive. After you pass 100, then you're going to be the angles that are going to be negative. So this guy will stay positive for a long time, negative for a long time. Okay, so I'm including these kinds of things. Okay, so we say the series sum of the ANs is absolutely convergent if the sum of the absolute values is convergent. Okay. So more to the definition. Okay. We say the series sum of the ANs is conditionally convergent if the series converges, but when you do the absolute values, it diverges. Okay. So the standard example here is the alternating harmonic series. K equaling 1 to infinity, negative 1 to the k plus 1 divided by k. Okay. This is conditionally convergent because if you take away the absolute values, you would end up with sum of the 1 over k. Okay. Okay, so I guess we have to make some kind of an argument here. So make a little observation. If this thing is absolutely convergent, then it is convergent, i.e., if the sum of this thing is converging, that implies that the sum of these guys is going to converge. Okay, so this is just going to be a little sleight of hand here. Okay, so given that this thing converges, okay, so we make kind of a trivial little observation here that the value of AN is sandwiched in between the negative of its absolute value and its absolute value, right? So 0 would be less than or equal to AN plus the absolute value of AN, and that would be less than or equal to 2 absolute values of AN. So if we were to let B sub n be this A sub n plus the magnitude of A sub n, okay, then my B sub n is sandwiched in between these two guys. Okay. Now, because it's absolutely convergent, this adds up to something, is convergent. Okay. So what does that tell you? It tells you that the BNs are convergent. Okay. Now, when I start inserting this stuff, the AN is equal to the BN minus the absolute value of the AN. Okay. So the sum of the ANs is equal to the sum of the BNs minus the ANs. Now we had that result from when we started that said if this converges and this converges, then the sum of the BN minus the AN is the sum of the outside guys, okay? So what that means is that this thing converges. Okay, so trip for you there. All right, so for example, a guy that might give you fits here, if you were trying to play around with it, sine of n over n squared. Now, if you want this to stay kind of plus, plus, minus, minus, maybe you'd let n be radians. If you let n be degrees, won't turn negative until after n is 180. But this thing is absolutely convergent. Because the absolute value of sine n over n squared, well, it's bigger than 0, less than 1 over n squared. That thing converges. So by the whatchamacallit thing, comparison test, thing's going to converge. Okay, now we know that the natural log of 2 is the sum from n equal 1 to infinity, -1 to the n plus 1 over n. We just established all that. Okay, you guys still with me?
Yeah.
Talking about, okay. All right, now this is conditionally convergent. In the 1800s, even in the late 1700s, people started recognizing that, you know, some sums add up faster than others. I mean, really fast. And this one was really slow. So they started doing investigating and stuff like that. So if I was to write this out, like the natural log of 2, I'll write out a bunch of terms here. 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus 1/7 minus 1/8 plus 1/9 minus 1 over 10 plus 1 over 11 minus 1 over 12 plus minus. Okay. So if I was to write down what 1/2 times the natural log of 2 would be, I would have a half right there. Okay. And then the next one would be a 1/4 that I would have right there, and it'd be a minus, right? Okay. And then the next one I would have would be a 6, right? And that's going to be a plus a 1/6. Okay. And then the next one I'm going to have would be minus an 1/8. Okay. And then the next one I'm going to have is plus a 1/10, and so on and so forth. Okay, now, if we were to add these two things up, we would have 3/2 the log of 2 equaling whatever this is. 1, that cancels, plus 1/3, that cancels, plus 1/5. Whoops, that didn't cancel. Go back. Got too excited. So I add these two things together. I'm going to get 1/3 here, and then the minus 1/2 comes, plus a 1/5, plus a 1/7, minus a 1/4, plus a 1/9, plus a 1/11, minus then a 1/6, plus minus. So what you see is happening here, this is a rearrangement of the 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6. So you see what's happening here? By rearranging the way that this infinite sum is adding up, now I can get it up to a different number. Okay, now this could be a bit disturbing. Leonard Euler didn't publicly think to question these kinds of things. I got to think, though, that a guy of his level, he knew more. I think maybe he was just trying to get done what people could understand locally. Gauss did stuff that people didn't understand until 100 years later. Riemann is another guy like that. Okay, so there's a result here, and Riemann actually proved this. That if this series B sub n is conditionally convergent, then for any real number r that we can think of, there exists a rearrangement of the series that adds up to this number r. So the proof, is very hard, obviously. Okay, but that's kind of an interesting thing that happened here. Okay, so get caught up, and tomorrow we will talk about the ratio test and the root test. All right.
What page is that proof on, real quick?
The rearrangement stuff.
Yeah.
Let's see. It's on page 737 in my book.
Okay. Thank you, Professor.
All right. So let's do this. See how many people are here. 34. That's not a bad number. Chat. Any questions from you? Do we have an exam tomorrow for sure? Yes. Exam tomorrow. I haven't made it yet because I didn't know what quite to put on it. Now I have an idea of what's put on it. So it'll cover the stuff from chapter 10 and a few of these. Hey, does this converge questions? Yes or no? All right. Let's see. I don't have any news from school. It was being pointed out today on my favorite afternoon radio show, Mason in Ireland, on ESPN, LA 710. Sounds like I'm sponsored, right?
You are, man.
So what they said is that if you're in Los Angeles you can't get tested for free unless you're exhibiting symptoms. Okay, so this explains why there's so many positive tests. People that are negative aren't going to get tested.
Yeah.
So I don't know.
It's frustrating, man. I mean, it's at this point, yeah, I mean, there's really nothing to do about any of it. Just wait for a couple years or whatever till enough people lose their jobs, and then maybe we'll go back to some semblance of normal. But
I will say this though, the first symptom you guys have to look for is the sore throat. Like you start losing your voice. I lost my voice before I even felt a fever, which was weird because I didn't. That was weird. So if any of you guys feel like you have a sore in the back of your throat and you start feeling like you're losing your voice, that's it.
yeah, but I also wouldn't be like too worried. I know there was like a ton of people who like they got anxiety attacks, and like I watched them on Instagram. They're like, "Oh man, I can't breathe. I have coronavirus for sure." And they go to the hospital and they waste like a whole day, and then they find out no, they had an anxiety attack. Or even this is the one I've only read about. I don't know what actually happened to anyone, but the worst one that I read about is them doing exactly that. Then getting in a bed next to somebody who has the coronavirus, and then they died from it because they were older. So, because the hospital will admit you, and the way it works, from what I've gathered, is they'll put you next to coronavirus patients. You're all very close. So, yeah, you will. Yeah, I mean, go to the hospital if you need to, but I'm just saying, like, I wouldn't. I'd prefer not to go. I mean, there's no real good reason to go, especially if you're under the age of 70. I mean, it's really
I mean,
low.
the only reason I would think of going is if you start having the breathing problems when you're calm.
Yeah, if you can't
not
breathe,
talking
yeah, for
like-
sure.
like, you know.
A friend of mine, I was the best man at his wedding. He's been in and out of the hospital the last few days. He was body surfing down near Main Street in Laguna,
Okay.
a little bit up north of it. His mom lived there for years, and it was a really low tide, and apparently down in that beach there's exposed rocks not near the jetty. And at the low tide, anyways, he pile drived his head straight in. I went over today. He's staying at his girlfriend's house. The doctor won't let him go home because he's a 3-story house.
Oh, okay.
And so he had to go to the emergency room. And then yesterday, I mean, it's a really bad concussion.
Okay.
But I'm looking in his eyes, and he might have some brain damage. I mean, he is not sounding right. Anyways, she called me to make sure I came and visited him today just to calm him down. So like, dude, just please wear the mask. The doctors will feel safer. Just get you in and out. It's like, so, but every time you go into a hospital or a doctor's office, that's the place where coronavirus people are.
Yeah. So the sick people are.
The actual sick people. It's like when you go to the pharmacy or you go to like a Rite Aid, you that's where the sick people are. So that I would emphasize, if you're going to a place that has a pharmacy, gloves and masks.
Yeah. I love it. There was a comedian that made jokes about it, like how silly it is that we have that women give birth at hospitals. It's like the place where most people go to die, but it's also randomly same place where we have like new people born. Yeah, I totally get it, but it is kind of a funny thing that's like, yeah, I mean, you generally don't want to go to the hospital. You can also check out urgent care if you're really, really struggling. And if you're just like worried, I think they occasionally set up those checkpoints you can do if you want to spend like 6 or 7 hours. I don't know if they're free, but occasionally I think they'll do free testing. I've heard they're just a mess, but I mean, some people want to do it. So like, I think if it's not free, I think it's like $50. So that means nothing to you. It's it's whatever.
Yeah. I got to check in on my buddy. He needs to be monitored 24/7 according to doctors, and he just went through a gnarly divorce. So
Ugh. The same guy who smashed his head?
yeah.
Oh, wow, man. And is he in a hospital or is he in a house?
They let him out of the hospital. So he went through a really ugly divorce.
Yeah.
Like, I was at football practice and I got a call. He had just left court. He goes, dude, can you help me? I have to move out of my house in 2 hours.
Oh, wow.
I had to drive from the football field up here in Costa Mesa down to Liso and get him all moved out, you know, by 7 o'clock or something. And so I've kind of lived through this whole thing with him. Their oldest kid has got some developmental issues, and he had been away at a boarding school, you know, behavior problems too. And Eric's ex-wife, his parents are very wealthy. And so they waited until Eric didn't know what was happening. Like, he did the body surfing thing last Tuesday. And while he was in the ER, they took Luke and they flew him to Wyoming and put him in another boarding school, not telling Eric they're doing this.
That's their grandson and your friend's son?
That's their grandson and my friend's son.
Oh, wow, man.
So Heather, the mom, thinks that it'd be better, but Julie and I are kind of, okay, you know, we'll put that fire out after we put out the brain damage fire.
Yeah.
You know,
That's a bummer, man.
so, but anyways, when I left today, he was going back to urgent care to have him look at the DVDs again, because he has this spleen. What happened this morning, he was standing up, going to the bathroom, and he fainted.
Oh, no.
And luckily she was there near him. This is a very small house in CDM. Like, but I know a dude that passed out in the bathroom, banged his head on the toilet and dead.
Yeah.
So if you're going body surfing in Laguna, just be careful. Like, there's,
Yeah, man. That's.
People are surfing right now with the red tide in.
I don't know. I didn't know. I mean, I haven't heard about red tide. My sister goes surfing every day. Didn't seem to.
Oh, maybe
red,
it's the patch that I saw.
well, he was surfing. He was body surfing.
yeah, red tide is up north right now. It looks like there was red tide in like April or May, but
Yeah.
it's gone now. It's normally a short term thing, I think.